Okay, how do I... Yes. Okay. Can this please make things easier for me? Okay. I've gotten a request to go through some specific problems. So I'm just going to wait for the person that requested them to join the stream. Still a bit confused by last time for the Fermat's Christmas Theorem stream. When I started the stream from OBS, it didn't start automatically on YouTube, but this time it did, which is weird. One day I'll understand. Cool. Okay, you're here. Fine. So oh, this is the solution. I guess I should look at the problem statement. Oh yes. Okay. The question was, what is the remainder when x to the 52 plus 201x is divided by x plus 1? Okay. What is the remainder when x to the 52 plus 201x is divided by x plus 1? And I'm assuming they mean as, well, it doesn't actually matter if you mean as polynomials or as numbers, because it's always the same thing. But I think they mean as polynomials because, okay, because there can't be such a large remainder for x equals 1. 202 over is divided by, yeah, okay, so fine. Cool. Yeah, they do mean when you... Okay, so what you should know about polynomials with coefficients, let's say real coefficients or rational coefficients, it works sort of for integer coefficients with some caveats, is that if you have a polynomial p of x and a polynomial, what do I want to call it? Because I want to use q for the quotients. I don't want to call the thing I'm dividing by q. Let's call it d of x for the dividend. So this is some polynomial. Nomial, and this is some polynomial, which is the dividend. And you can do division with polynomials basically in the same way as you do with natural numbers. You're going to get a quotient and a remainder. P of x, you're going to be able to write it as the thing you're dividing by times a quotient plus a remainder, where the degree of the remainder is smaller than the degree of the thing you're dividing by. Yeah. This is technically, for this to be correct exactly how I've written it, you're going to have to define the degree of the zero polynomial to be like minus infinity or something. So what you sometimes just see people say is or r equals 0, because sometimes people leave the degree of the zero polynomial undefined, but they mean the remainder. Like when you do the division with polynomials, they mean the polynomial that makes this identity true. They don't mean that this is that you get this is the they don't mean that this is the remainder you get for every integer that you plug in. They don't mean that p of x is, they don't mean that this is some number and this is some number. What is, what is the remainder going to always be? Because like you point out, okay, now as an, yeah, the question isn't asking what you think it's asking. So for x equals 1, like you pointed out, you're going to get 202 divided by 2, and you're going to have a remainder of 0, which is definitely not 200. They don't mean, yeah. What you'll learn much later on in your life, although maybe it's useful for you to know it now, is that if I take a polynomial, let's do a small example. If I start with something like x to the How do I get to... No, this is just like the definition. This is the division theorem for polynomials. Um, it's sort of guaranteed that for polynomials. Yeah, P and D are given, and what the theorem says is that you can find a Q and R that makes this true. So let's make that explicit. P and D are given. Then there's a theorem that says that you can find Q and R that make this true. Yeah, so P would be that x to the 52 plus 201x, and the D is the x plus 1 that we're dividing by. And they mean that this is like, that you get the same polynomial on both sides of this thing. Usually the way that you do it, and basically the reason why the theorem is true, is that you can do polynomial long division. So if I started out with something like x cubed plus 13x squared plus 9x minus 4, and I want to divide it by x squared plus 7, I term by term, I find what I have to multiply this thing by so that the first term matches the first term over here. So if I multiply this by x, I'm going to get an x cubed plus 7x. And so I'm going to be left with 13x squared minus 7x plus 9x minus 4. And now if I need to multiply this by 13 to make the leading terms match up. And I make the leading terms match up so that I'm decreasing the degree of this remainder on each step. So plus 13x. I'm going to have 13x squared plus 91x. And then I subtract, and I get minus 98x. Oh, this should have been... I've already done something stupid. So this minus 9x, minus 7x plus 9x is plus 2x. That doesn't really matter. I still get the 91x over there. This 13x squared was right. So the thing I have to multiply by to make the initial terms match up is still 13x. And so when I subtract these, I don't get minus 98, I get minus 89x minus 4. And so you're then able to write down that x cubed plus 13x squared plus 9x minus 4 is equal to x squared plus 7 x, it should be plus 13, sorry, and then plus this remainder. And so this is the p in this context. This is the thing we're dividing by, the d. This is now the quotient that we get. And this is the remainder, which has a smaller degree than what we're dividing by. So we were dividing by something quadratic, and the remainder is then going to have degree 1. It's going to be something linear. And basically the reason this theorem is true is because you can do polynomial long division. You can divide and make the initial, you can always make this initial term match up by multiplying by something appropriate. Now, I said there's some caveats here. If you're doing this with polynomials where the coefficients are integers, you're not guaranteed that the quotient and the remainder are going to have integer coefficients. You are guaranteed that if the thing you're dividing by, if this leading term is 1, then you're guaranteed that the result is going to just have integers in it. But if this leading term is not 1, then sometimes to get these, these leading terms to match up, you're going to have to multiply by a fraction and not by an integer. So if I wanted to divide 7x squared plus 3x plus 9 or something by 2x, the procedure is I try to get these first terms to match up. So I'd have to multiply by 7 over 2, 7 over 2x, so that I get a 7 over 2, a 7x squared that I can can subtract. And then I'm left with 3x plus 9, and then it's plus 3 over 2. And then I get 3x, and then I'm just left with 9. And you're going to see that then you have a remainder of 9. But the division works the same way as it does for numbers, basically. It's the same algorithm. You divide the terms one by the thing that you're dividing by, and then carry the remainders forward. And as long as you're in a setting where you can divide by this leading coefficient, you can always, yeah. Well, if you've ever worked with polynomials before, this is the standard, the standard nomenclature. When this is the natural way to interpret this question. It's I can understand that if you haven't done polynomial like long division in school yet, then you might think that they mean, x is some fixed number. I divide it by this other fixed number. What is the quotient or what is the remainder? But if you substitute different values for x, you're going to see that you get different numbers each time. When x is very big, no, actually, I think, yeah, you never. We can probably say something about what the possible remainders are when you like interpret this as some integer divided by some other integer. Now the trick here for this question actually is the fact, I don't know what it's called. It's not the factor theorem. It's like the remainder theorem or something. But if you divide by, yeah. So why they substitute is that if d is linear, right, i.e. the degree of d is 1, then what the theorem says is that we can write p of x is equal to q of x d of x, so the quotient times the thing we're dividing by plus some remainder, and the degree of the remainder is smaller than the degree of d. And so this means that that this remainder either has to be 0 or it has to have degree 0. In other words, it's constant. And in both cases, that means that this is constant. So the degree of the remainder in this case is less than 1, so r is constant. It always has the same value. Right. So in our case, we know that from the theorem, we can write x to the 50, and that constant you can get by, plugging in. The easiest value to plug in is the one that's going to make this equal to 0, so that this just goes away and you're just left with the remainder. So the way that you sometimes see the theorem stated is the remainder as a polynomial. The remainder when p of x is divided by x minus a, x minus a is p of a. And the reason for that is, again, by the polynomial long division, we can write p of x is equal to x minus a times some quotient plus a remainder, and because the remainder has to have a smaller degree than 1, we're guaranteed that the remainder is a constant. And so plug in a, and you get that p of a is, I keep pressing the erase button, is equal to a minus a q of a plus this remainder, which is a constant, and that's just r. And so this remainder, when you divide by x minus a, is what you get when you plug a into p. So in our example, we've got x to the 52 plus, what was it, 201x or something? Yeah, 201x is going to be x plus 1 times some quotient. We don't have to work it out. We could, if we wanted to, we could divide this by x plus 1 and see exactly what we get. I don't really want to. Plus some number. It's a fixed number because the degree of this is smaller than the degree of the thing we were dividing by. And so plug in -1. I don't know why they did that. That's not necessary. Yeah, I don't know why they did that. You can get away without doing it. And you get that 1 minus 201 is equal to r, i.e. r is minus 200. Although I think they just get... Why do they get... x plus 1 q of x? Oh. Why did they... Why did they do... I don't know. Maybe the question is different than what you wrote here. What is the remainder when that is divided by x plus 1? No. Yeah, if they divided by that x, they're doing this wrong, unless the question was different than what was asked. Okay. Yeah, if it had to divide it by x, then yeah, you would divide by x first. That's fine. Yeah, sure. If you did the same thing with x to the 51 plus 201, then you're going to, like the sign is wrong because we had this extra factor of x over here, so we then multiplied this side by x, which is -1. And so that's why you get -1 times the answer that they had. Yeah. If you wanted to work this out explicitly, you could well, if you wanted to do it the long way, you could, you could go through the whole process of dividing this by x plus 1. So we're going to have a x to the 51 over here. This gives us x to the 52 plus x to the 51. We subtract, we get minus x to the 51 plus 201x, and then you match these up again. So we have minus x to the 50 plus blah, 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 blah. And you're going to, if you keep going, you're going to get a remainder of minus 200 eventually. The easier way to do it in this case is we know that x plus 1 is a factor of x to the 52 plus x, because this is x times x to the 51 plus 1, and this is divisible by x plus 1. So this is x plus 1, x to the 50 minus x to the 49 plus x to the 48 minus x to the 47, and so on, plus 1. And so we're going to get that x to the 52 plus 201x is x to the 51 plus 1 plus 200x, which is then x to the 51 plus 1 plus 200 times x plus 1 minus 200. And then when you can do the, you can take out the x plus 1 here. It's x plus 1 times x to the 50 minus x to the 49 plus x to the 48, and so on. 40. Why is this not writing anymore? I hope this is not going to become a problem, because I don't have any more batteries. I need to order some. X to the 48 and so on plus 1, and then plus 200, and then minus 200. So you can see that you don't have to work this out, but just as a demonstration that the theorem actually works. Here's our dividend thing we're dividing by. This horrible thing here is the quotient that we were promised exists, and here's the remainder. And yeah, if you did the long division the long way around, you would also get this. This comes from the formula for like sums of odd powers. So x to an odd power, let's call it n plus y to the n is x plus y times x to the n minus 1 minus x to the n minus 2 times y plus x to the n minus 3 times y squared, and so on, minus blah 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 plus uh, x squared y to the n minus 3 minus x y to the n minus 2 plus y to the n minus 1 if n is odd. No, the degree of the remainder is always, you're always guaranteed to be able to find a quotient and a remainder that makes this equation true, and that has the property that the degree of the remainder is smaller than the thing that you're the degree of the thing that you're dividing by. And so as a special case, when it's linear, you're guaranteed that the remainder is constant. Now there's if you don't insist that the remainder, so to speak, is going to have a smaller degree than the dividend, then this representation stops being unique. You know, you can write x squared plus 1 as, you know, x plus 1 times, so the quotient remainder version is going to be this. Here's the quotient, here's the remainder. But if you don't insist that this has a smaller degree than this, you know, this is also x plus 1 times x minus 2 plus x plus 3. So it's possible to write it in a different way, where the remainder, like it's not actually the remainder, where this extra piece has a degree that's too large, but that's not interesting. The interesting thing is that you can write it in a way where the remainder does have a smaller degree than the thing you're dividing by. Like there is a version that exists with the remainder being small, and where the appropriate notion of what it means for a polynomial to be small is that it has small degree. But yeah, it doesn't mean that whenever you write p of x is q of x times d of x plus r of x, that the degree of the remainder is always smaller than the degree of d. It's there are q and r that make the equation true, where the degree of the remainder is smaller than the degree of d. And that's usually the case you're interested in. That's, you know, it's interesting that that happens. It's not interesting that you can write this as a sum of other polynomials. I can write this as the sum of two different polynomials in infinitely many ways. It's you know, as many ways as you can dream of. I can write this as x squared minus 1 plus 2. I can write it as x squared minus 7 plus 8. I can do lots of things, but they the theorem guarantees that I can also do it in such a way where this extra piece that's left over has a small degree. Okay. They probably won't ask this sort of thing in the South African Maths Olympiad. I've never seen it. If what we can work out from this, I guess, is that we can get some bound on the remainder when we plug actual numbers in and we divide the numbers. So we know always that so we have this x to the 52 plus 201x is x plus 1 times q of x plus minus 200. And so that means whenever I plug actual numbers in, oh, this was from Samo. How long ago? I don't think it's probably not recently, surely. Because I don't think they, I mean, South African schools are useless, so they don't teach, I don't remember them teaching this in high school, but I remember it being in like AP Maths and maybe I don't know. I'm surprised. 2013. That's even more surprising. That was before the curriculum change, I think. Yeah, it was still like the NSC instead of CAPS or whatever. I don't know. I don't speak South African Education Department. Not fluently anyway. If you do plug actual numbers in here, this equation's still going to be true. So the remainder when you plug actual numbers in is going to be the same as the remainder when you divide 200 by x plus 1. So remainder for actual numbers is the remainder when you divide 200 by x plus 1. And that's because with actual numbers, you can then carry on with the, like, what this is saying, as polynomials, this is saying that x to the 52 plus 201 x is congruent to minus 200 mod x plus 1. And so if you plug in any actual value for x, an integer value for x, this is still true. You still get that x to the 52 plus 201 times x is congruent to minus 200 mod x plus 1. And so the remainder, when you divide this by x plus 1 with actual numbers, like 200 and the actual remainder that you're interested in are the same modulo x plus 1. So x plus 1 must be, yeah, it's the same as the remainder when you divide 200 by x plus 1 for actual numbers. So for x equals 1, the remainder when I divide 200 by 2 is 0. But if I were to plug in 57 for x, the remainder when I divide 200 by 58 is, I don't know, 40 something, because 3 times 58 is 150, 174, and then I'm left with 26. Yeah, so 26 if I were to plug in 57, for example. So it's not going to be a fixed number, but we do know something about what that number is going to be. Okay. The circle question you ask. Let's copy the circle question. Paste. The diagram shown is formed by extending the sides of a right triangle and constructing 4 circles that are each tangent to all 3 sides. Yay. Okay, so the in circle and the 3 x circles. The radii of the 3 smaller circles with centers at D, E, and F, great, are equal to 3, 14, and 21. And what is the length of the radius of the circle with center G? So there is a formula for this. So it's mean of them to put it in, to then ask this. I think you get something like 1 over the n radius is equal to 1 over the sum of the x radii, if I remember right. So if you already knew this, then you can answer this question very quickly. But otherwise, I mean, this comes actually from considering the area of like some triangles. But let's look in radius x radius formula, just to make sure I've got this right. And then I'll try to explain where it comes from. Yeah, it is 1 over the n radius is the sum of 1 over the x radiuses. So what I mean by that in this case is that 1 over the radius of that smallest circle, the one with the center at D, is equal to, what it means in this case is that if this radius here, let's draw it like that, is x, then you get that 1 over 3 is equal to 1 over 4 plus 1 over 21 plus 1 over x. And then, like I said, that's going to be by far the easiest way to do this. Okay, let's prove the formula in general, because the way to do it then, the easiest way to do it is probably going to be to this is weird. I thought it just came from like considering areas of triangles, but I mean, I could be wrong. In this case, maybe it's possible to do it just with like coordinates, or the radii of the 3 smaller circles are 3. Yeah, because this is a right angle triangle, there's a lot of things you can say already. That length's 3, that length's 3. that length is 3. We know this is a square. 4 and 21. Yeah, like the other thing that there was like a way to relate. It's the length of this line is equal to the length of this line, I think, which is also unfair to expect you to know. Well, maybe, I don't know, like maybe it's not unfair to expect you to know it, but there is a lot of things that are known about in circles and X circles, and this is one of those things. I'm just trying to see what the best thing to do is going to be over here. So if that's 3, actually I have no idea. Let's prove a whole bunch of facts about in circles and X circles, I guess is probably the, and then I'll try to remember where that formula comes from. That's not what I want. I want to, these circles are going to not be very, okay, I should have, this is not going to be a great diagram for this. Okay, so we've got that circle, we've got that circle. That's a circle, an artist's impression of a circle. It's, yeah, so if this length is x, you know that's also x, you know this is y. If this, then this length is also y. And we also know that if I, and if this length is z, then this length is, this whole length is what I'm calling z. Then this is also z. And I know that this whole length that I'm going to highlight in green is equal to this whole length that I'm going to highlight over here, because they are tangents to a circle. And also, so this is going to be equal to this. So let's give that a color. This thing in red is equal to this piece in red, and let's call that A. And A and blue. This piece in blue is equal to this piece in blue. Let's call that B. And so we know that x plus y plus A is equal to x plus z plus B, from which we get, yeah, y plus A equals z plus B. What else do we know? We know that A plus B is y plus z. So yeah, this gives us two equations that we can solve then. So we know A plus B is y plus z, and A minus B, at least in this diagram where A is the longer one and B is the shorter one. Sorry, is going to be A minus B is Z minus Y. And so you can work out explicitly that A is equal to A is equal to Z and B is equal to Y. Actually, yeah, that's just always true. There's nothing I've used about this setup in the diagram. So this length here is Z, and this length here is also Z. And so it's in general true that if you have a triangle and you draw the in circle and you draw the X circle, and let's say that it's tangent over there, that's very unrealistic. But what you're always guaranteed is that that length in red over there to the tangency point with the in circle is equal to that length over there in blue. And the leftover pieces are then also equal. You get that this green piece over here is equal to this green piece over here. And I guess we can apply that in the question that they asked us, because it means that this piece over here is has got length 3. And so this like length to that vertex is a 5. And I don't know, maybe this goes somewhere. Maybe it leads to something useful. Maybe it doesn't. The easiest way definitely is if you, by chance, happen to know this formula already. Where does it come from? R over... I'm actually not sure. I think it comes from something like... wolves, like... it turns out that like the area of this triangle is r times the semi-radius, but like that means that 1 over r is going to be like x plus y plus z divided by the area of this triangle, and like I don't see how that's going to turn into something nice. But I swear that this formula just came from like manipulating areas of triangles in this figure. I just can't remember which ones. But yeah, if you maybe knowing this fact about the lengths of the tangent lines to the n circle and the x circle might have been enough to work out what all the coordinates are of the interesting points in this diagram. And then you can set up a whole bunch of equations. I don't know. Uh, but yes, if this is a question where if you already know how to do it, then you can do it very quickly. I guess that's true for every question, that if you already know how to do it, you can do it very quickly. Yeah, where does this formula come from? It probably also comes from... So is that like the only use case of this formula? Yes, is this one question that we asked once in the SAMR round 2. It's the only time it's ever been used. No, I don't know. None of like the geometry stuff you ever really see again after school, but it's useful within geometry. It is a formula that allows you to... I think it's also got to do like with where the center of mass is of appropriately placed masses, because the barycentric coordinates of the in center is ABC. So it's like if you place a mass of... I forgot what the masses have to be, but if you place like the appropriate masses at these points, so if this side of the triangle was A, B, and C, and you placed in the mass of... I think it's like A at this vertex, and a mass of B at this vertex, and a mass of C at this vertex, then the center of gravity turns out to be at the in center of the triangle. And maybe there's like some consideration like that also, this formula might say something about that. Not sure. Trying to remember what the way of doing this with areas is. It's like 1 over RA is a very weird quantity to have. It implies that something divided by... I mean, I guess what we also know is that, but like where do we draw the lines? Because I was going to say that there is like these circles are similar to each other. Let's draw that. Let's draw this. Maybe that's where the formula comes from, actually. So maybe we're about to prove it. Let's take these points of tangency. Let's call these x and x, y, y. Oh no, they're not similar. Never mind. Oh, no, 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 they are. So if I join, yeah, if I join those to those. So if I have this blue triangle and this purple triangle, they are similar. Because the ratios of these lengths, it's x to x plus y plus z, right? Because we know that this is y and this is z from what we were doing earlier. And so that means that if you consider like well, let's use the fancy word, the homothety, the transformation that scales this triangle up by a factor of x plus y plus z over x, it turns out that it also maps this circle to this circle. That's not immediately obvious, actually. I'm sure that's true, but I'm not actually sure how to justify it. Because I guess we'd have to know that. And actually, that's not true because we have to. Maybe, I don't know. Maybe it's true, maybe it's not true. Um, actually, maybe, yeah, the other important thing maybe is that the centers of these circles are both on the angle bisector. Yeah, so if I draw in that radius, actually, and that radius, those are, yeah, actually, yeah, fine, it is true. What I wanted to say is true. But I think it's because the centers of these circles are on, we do need this fact that they lie on the angle bisector. So this radius, and let's call this RA, we get that R over, so these two triangles are now, so it's actually this blue triangle that I'm interested in, and this purple triangle are probably easier to justify why what I'm saying is true. So these are 90 degrees because the angle, the the radius is perpendicular to the tangent, and yeah, they've got this common angle up there, so they've got two angles equal, so they're similar. And we know what this ratio is. We know then that R over RA is equal to x over x plus y plus z. Okay, and we're going to, so let's gather everything that we know then. And then after this, I'm going to have to stop because I actually have to do something now. But we get that R over RA is equal to x over x plus y plus z. And from the same consideration, you're going to get R over RB is y over x plus y plus z. And R over RC is equal to z over x plus y plus z. Okay. And so if you add these together, you see that you're going to get 1. You get that R over RA plus R over RB plus R over RC is equal to 1, which is exactly the formula that we had, because now we just divide both sides of this by little r, and we get that 1 over 1 over 1 over and 1 over r. So it actually comes from similar triangles. It comes from realizing that this triangle there of A to the x center opposite A to this tangency point is similar to this triangle over here. But then to get this ratio, I also needed to know the other fact that most people don't know about in circles and x circles, and that's that this the length of this line segment over here is equal to the length of this line segment over here. But oh well, now you know. So now you can also, yeah, potentially answer a question in 2 minutes in the future. It is. I'm going to agree that maybe it's an unfair question for the second round, but this formula is, I think, I don't think we would have any issue with including a problem in the third round that relied on you knowing this formula, to be honest. I think this is fair game. But anyway, I think, yeah, I'll say goodnight then, and cool. Maybe I'll do this again on Sunday. You can send questions again if you want. Yeah, good night.